Hey there, it's Modern Retro Tech, and today we are continuing with Advent of Code Streams. We will be reviewing my solution to day 19, then we will hopefully solve day 21, and we will review the first part of the day 20 and also hopefully solve the second part of day 20. So we will be solving stuff as usually in Rust. Oops. Second, I am having some weird echo of myself, which is a bit weird. I will just quickly find this tab. Yeah, so, okay, the tab has been found and killed. Okay, sorry about that. So yeah, day 19. I will quickly walk you through the task and then we will start talking about the solution. So I will skip the lore. Essentially, you get like messages that you need to decipher. Yeah, they sent you a list of the rules valid messages should obey and a list of received messages they've collected so far, your puzzle input. The rules for valid messages, the top part of your puzzle input, are numbered and build upon each other. For example, 0, 1 followed by 2, 1A, 2, 1 followed by 3, or 3 followed by 1, 3B. Some rules have just a letter, so they just match the letter, and some rules have a sequence of other rules that they can match, and they can also have alternatives. So rule 2 matches either 1 followed by 3 or 3 followed by 1, where 1 is just letter A, 3 is just letter B. So rule 2 can match either AB or BA. And rules can build upon each other this way. Fortunately, there are no loops in the rules, so the list of possible matches will be finite. Then they explain a bit more about rules. They show another example with a bit more complex rules. And in the end, what you get is an input where you get those rules, then empty space, a blank line, and then you get messages. And you need to calculate the number of messages that match rule 0. So that was immediately obvious that this is a task about regex, regular expressions. So here you can see that even syntax is very similar to regular expressions. And that's what essentially I went with. Now, one interesting thing about part 1 is, of course, that you don't get like regular expressions that you can just compile and apply with your normal regular expression engine, right? So instead, you need to kind of take those rules and convert them to regular expressions. In this case, puzzle input looks like that. So it's quite a long list of rules, and then you get a lot of messages. So overall, there are like 633 lines of code here. Which means that if we will try to naively match it by hand, that can take quite a long time. Instead, we should use regular expression engines that we have. And that's exactly the solution I went for. So first, as typical, I did parsing. Parsing is pretty typical. It's not really different from all the other parsing logics that we wrote before. So I won't really stop on that much. The main thing is that we get essentially 2 vectors from that. We get a vector of rules and we get a vector of strings. And vector of rules, each rule is an enum, and it has 2 options. It can be either just a letter, which for simplicity here is represented as string, so we know that it could have been also HR. And it's also, or it's a vector of alternatives, where each element of this vector is also a vector with a sequence of rule numbers that we need to obey. Of course, since rules are put into vectors, those numbers are just indices in the vector with all the rules. So that's how we represent our input, and I guess messages themselves is quite obvious that it's a simple vector of strings, nothing fancy there. Once we've done that, we start to solve things. So I wrote a function called expand, which accepts a reference to the vector of rules and index, the rule we actually need to expand. And we call a function called expand inner, passing the rule there and also reference to the rule we are expanding. And then if it's a letter, well, we just convert it to a letter, because in regex syntax, letter matches itself. If it's a list of alternatives, then we go through all alternatives, and each alternative we expand. We collect them to a vector, and we join them together. So one single alternative is a sequence of other rules. So we just put each expanded rule after another. And then all alternatives we join with this same pipe symbol that is used in our input, which in regex is just alternatives, essentially. And if we have only one alternative, then we don't need to put this pipe symbol. We just join the instances of rules that we got there with empty space. So this way, we convert from the input that we got to a regex, essentially. And then we just need to compile it and apply it. Which we do, we add a condition to that the whole string should be matched. So in regex, this means that the start of the string should match, and this means that the end of the string should match. And between that is our expanded expression. Then we use normal create regex, we compile the regex, and then we go through messages. And if message is a match, we count it in, and then we report the count. So of course, that runs quite fast. And that solves the first part. We got the number 224. And that's exactly our answer. Next is part 2. So here the trick is that rules change, and now loops are allowed. But we have only 2 instances of rules, of loops, essentially here. So we need to replace rule 8 that is now just matching rule 42, and rule 11 that is currently matching rules 42 and 31, with the different formulations. So rule 8 now matches either 42 or 42 followed by application of rule 8, essentially matching one or more instances of rule 42 if you expand it. 11 is a rule that matches 42 followed by 31, or it matches 42 followed by rule 11 itself followed by 31. So that works like essentially parentheses that need to match. Yeah, they mentioned that loops are now contained there, which means that we cannot use typical regex to actually solve the task. We need to add some logic on top of that. Now, there is one important piece of internet lore that I will mention. There is a famous question on Stack Overflow, regex match open text except HTML self-contained text. And somebody wrote this majestic answer. So you can't parse HTML with regex because HTML can be parsed by regex. Regex is not a tool that can be used to correctly parse HTML. So in essence, he talks that you cannot match non-regular language with regular expressions. For example, if it contains loops or things like match parentheses, you cannot normally use regex to match it, and you shouldn't even try. And of course, it escalates, and this is like historic post that is still rather fun to read all those years later. And here, of course, if you try to use regex, there are some regex engines that allow you to do stuff similar to that, but it will be not fast and it will be quite painful. Instead, what I decided to do, I decided to use several regexes and add a bit of logic on top of that to still match stuff. So in essence, we take the rule 42, we expand it, and we got something. Let me quickly just do a bit of debugging here. So that you can see how it looks. Here's the same with rule 31. So I will quickly recompile this thing. So now if we apply 19.2, we got those crazy regexes. And as you can see, this is still normal regex. I use non-caption groups everywhere to avoid caption stuff, and I will talk about caption in a second. So this is our rule 42, and this is rule 31. They're non-recursive. So just essentially much complex sequence of A and B characters. That's it. Now, once we extracted those, we know that new rule 8 just requires it to repeat 42 one or more times. Rule 11 requires that to have balanced number of 42 and 31. If we look at our starting rule, which is still rule 0, we will see that I'm using regex also to search here, but here, it's just a rule 8 followed by rule 11. And this is central, of course, to our solution. It means that we just need to match the same number of 42 and 31 strings that are matching regexes 42 and 31. And we can have additionally, we need to have at least one additional 42 in front, or we can have more than one in front additionally. That's essentially what we need to match. And that's what I explained here as well. So 8 is now 42 one or more times. 11 is now 42 recurs 11, 31. This is our entry point, which means that the whole match condition is now essentially we start a string, we have 42 repeated one or more times, and then we have matching number of 42 and 31s. And the logic then becomes we first match 31s because that will allow us to infer the number of 42s that we need to match. We match 31s using this regex. We count the number of those matches, and then we just need to match 42, which should be the same number of matches plus one or more, essentially. And that's what we do here. So that's why we have 42 non-capturing rule. We have also capturing rule 42. We have capturing rule 31. Then we create start 42 and 31 rule, which is for the whole string, where it essentially says that we have we need to start with 42 rule. We take rule 42 non-capturing. We create a capturing group that we call start 42. We have rule 31 non-capturing. We put it as a capturing group and 31. And we know that both of those should repeat one or more times. We create a new regex from that. And then we call function matches new rules for each message, which returns a boolean. So then we can just also do a count and we will get our answer. So matches new rules is, it checks that this basic regex is matching. So the string looks like something that can match in principle. Then it iterates through the captures. If we captured one instance of that, we know that we can apply the rule 31 on the N31 capture, and we can count it. And then we can count rule 42 in the start of the string. And then if count 42 is equal, larger than or equal to count 31 plus 1, we know that the answer is yes, the rule matches our, the message matches our new rules. And that's essentially the whole task. It's not super complicated. I think it was one of the easiest tasks to solve for me, actually. Day 20 was a very different story, though. Then day 20, I still didn't solve the second part, and I will attempt to solve it in the end of this stream. The beginning I solved after much struggling. I went a rather complex approach there, but about that we will talk later. Now I want to start with solving day 21, and then if we will have enough time, we can try to look at day 20. So, day 21, allergen assessment. You reach the train's last stop and the closest you can get to your vacation island without getting wet. There aren't even any boats here, but nothing can stop you now. You build a raft. You just need a few days worth of food for your journey. You don't speak the local language, so you can't read any ingredient lists. However, sometimes allergens are listed in a language you do understand. You should be able to use this information to determine which ingredient contains which allergen and work out which foods are safe to take with you on your trip. You start by compiling a list of foods. You puzzle input one food per line. Each line includes that food's ingredients list, followed by sum of all of the allergens that food contains. Each allergen is found in exactly one ingredient. Each ingredient contains 0 or 1 allergen. Allergens aren't always marked. When they are listed, as in contains nuts, shellfish, after an ingredients list, the ingredient that contains each listed allergen will be somewhere in the corresponding ingredients list. However, even if an allergen isn't listed, the ingredient that contains that allergen could still be present. Maybe they forgot to label it, or maybe it was labeled in a language you don't know. For example, consider the following list of foods. So we got like some nonsense, which then contains dairy, contains fish. More nonsense contains dairy. Nonsense contains soy. Nonsense contains fish. The first food in the list has 4 ingredients written in a language you don't understand. Those are like instances of those words. While the food might contain other allergens, a few allergens the food definitely contains are listed afterwards, dairy and fish. So those must be present in this first line, but we don't know if there are any more, apparently. The first step is to determine which ingredients can't possibly contain any of the allergens in any food in your list. In the above example, none of the ingredients blah 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 can contain an allergen. Counting the number of times any of these ingredients appear in any ingredients list produces 5. They all appear once each except SBZZF, which appears twice. Determine which ingredients cannot possibly contain any of the allergens in your list. How many times do any of those ingredients appear? Okay, it looks also a bit like constraint satisfaction, but given my experiences with trying to implement backtracking for day 16 or 17 and my struggles yesterday with mean conflicts for day 20, I think I won't try to go this road. Another thing, of course, we can figure it out, right? Let's try to figure it out by hand and see how we can then attempt to write a program that does it. For those who are joining now, we are solving Advent of Code Day 21, Part 1, allergen assessment. We need to figure out which parts of this nonsense are not containing any allergens, and we have those instructions for which line contains which allergens here, but it's not exhaustive, so some lines may contain more allergens that I mentioned here. So I guess, so this thing contains dairy. It happens on the first line and on the second line. If we intersect those sets, we will get this thing as the only thing that is matching, so it's logical to assume that this probably is the dairy thing, I guess. With fish, we have this and this. Can we intersect this? Yes, we get this as fish-containing thing. So we figured that this and this can possibly contain stuff. Then, of course, contains soy. So we got this and we got this. In principle, this can contain soy because it's not required for this line to mention it. This, however, contains fish. In principle, this thing can also contain fish. So that may be also soy. So about this thing, we actually don't know. They both may be soy, which means that we cannot really exclude them. Now, we definitely know that this contains some allergen then. This one doesn't contain... This one contains stuff, for sure, I guess. And this... what contains dairy? I actually got now confused. This is dairy, I guess, and this is probably fish, or this is fish. Okay, for me it looks like we need to intersect those sets and see what we get. None of the ingredients, so this doesn't contain any allergens. Okay. And this doesn't contain any allergens. And this... Okay. Contains dairy, contains fish. For me, it looks like really it's just like set intersections. Set intersections. So we can try to just calculate it and see if we get the answer, I guess, at the first step. So it's typical, we are using our beautiful REPL interface to create day 21. And then we can get our puzzle input. So there are only 41 lines here, but those lines are pretty long. We will start with parsing stuff as usual. So I will make it a bit smaller so we can refer to it when we need it. So how do we want to represent it? I guess we can just use line numbers to refer to lines. So we'll have like a vector. And then we will have like hash set for each line which contains allergens and which contains foods. And then we will see what we get from there, right? Okay. So we get the reference to string. Let's define a type for this. So how do they call it? Ingredients list. Well, I learned almost all of them except for how to enlarge it for the whole string. It will be a vector of, yeah, we will need hash set. Hash set is the main hero of this advent of code. We will need it again, which will be it will be actually two hash sets, right? It will be a hash set with all our ingredients, and it will be a hash set. Actually, let's create a little struct because otherwise it may become confusing quick. So this will be a hash set of just string. And then we will have allergens, right? Well, I know what I will need. Let's derive stuff. So we'll need debug. We'll need clone. I'll just code list. Thankfully, it's not a reserved word in Rust, so why not? Which we will then will be just a vector of list item, right? And this thing then will return this list. Now we just take the input, trim and we split by new lines first. Right, we'll create a mutable vector here. And here we will start putting stuff there. So for each line, we can split it by contains, I guess. Yes. So that will give us a simple split point. And all of them contain something, right? Seems so. Yes, all lines contain something. Okay. So it will look like that. And we also will need to do trim and matches. No, I think there is also some trim. Okay, trim and matches, where we will just remove this thing because we don't need it. And then here we can then do, actually we can just do this. We can say parts, and then we'll need to declare it mutable because this is an iterator. Then we just do this will be, first thing will be ingredients. I think not sure that I'm writing this correctly, so let's do this. Ingredient, okay. Ingredients. So if we got ingredients and then we get allergens, right? Allergens. Oh God. Okay. And we just do parts next, and we do parts next. Actually, when I think about it, yeah, I think that's correct. Okay. Yeah, we of course need to return list from this thing. And here, so ingredients we split by comma, by space. Then we can do split ASCII white space. I think it should be a bit faster. And we just collect it to a hash set. Oh, I wonder if they can repeat themselves. So like, I think they don't, but I'm not sure. Did this thing repeat itself? I don't see any repetitions. I think they always are uniquely ones. So this thing appears twice, but it appears twice in different lists. Okay, I think we can use hash sets. I think it should be fine. So that will be, right, ingredients. So this we split by commas. And we also collect it into a hash set. And then we just create, you know what? Let's just call it item. And we just push it into the results vector. Found struct. Oh yeah, we need to map them to strings. Sure. And I think we parse stuff. So we can then take our magical input. Actually, yeah, we can already start writing it here. And we can debug it and see what we got. One thing that I changed, I switched my tasks to release profile because for, I think, tasks 16 or 17, otherwise they would take too long. But, oh, I already see a little error here. We need to remove spaces, right? Because in the case of allergen lists, they have space after comma. So that's a thing for sure. And we can actually also do so now it looks good. So let's check last line. Contains shellfish, feet, sure. And then we got a bunch of things. So it starts with this, well, it doesn't start with it. It contains this Q and VX. It does. And then XTGP. And then let's check that this thing contains this thingy. Yes, it does. So, okay, for me it looks correct. So now, what do we do? How do we solve this thing? I guess one way would be to try to intersect the sets and see what we get, right? We need somehow also to associate presences of things with where they are. If we go with plain set intersection here, we will get like options for each thing that can contain something, right? But how do you... So we have like a list of things that can possibly contain something. Contains diary. Like the fact that this appears here doesn't really influence anything. But then this will, for example, how do we infer QFCDS? If we intersect, so QFCDS only appears in the first item, right? And it can, in principle, contain diary. But then we get MXMXVKT, which probably contains diary, I guess. Okay, let's try to intersect things and see what we get. So we don't need to debug lists anymore. We can just try to get every allergen matched with the things that can possibly contain it, right? We probably will also need to have like all allergens, right? Actually, we may need to have a hash map from allergen to ingredients when I think about it. Let's be a bit shorter. So allergens to ingredients, what will it contain? Essentially, need to go through the list. Actually, that will be even... Let's do it like that. So you'll get like hash map, which will be new. Let's make it mutable. Do we need to do it like in both directions? Let's just create both of those and see what they will contain, because maybe it will give us a bit more insight into what we actually need to do, right? I wonder if I can do that. Oh, of course. Yikes. That looks not very nice. Okay, I will just better do item, I guess. Then for each allergens, we need to add an entry into first hash map al to inc where we have this will be like a hash map from string to a hash set, right? Because we will have like a bunch of entrants for each ingredient, and we will just need to have those who are there. Okay, so auto inc. So let's input an empty hash set. That will be as inks. Oh, or insert. So, and this will be like a mutable reference to the entry. So we can use it to insert our in item allergens. Like each of the ingredients can contain this allergen, right? We don't know at this point in time. So we can just put it there. Okay, I guess that covers the first hash map. Now the second hash map. So ingredients to allergens. We're going for each ingredient here. And we can do the same thing, right? So we can then do and then, so we got the entry. And we can just insert allergen. Okay. Iter. So let's see what we get. So we got those allergen to ingredients. And let's do this. And then we can look at like specific allergen, right? Maybe it also makes sense to look at our sample input because I think it will be a bit faster, a bit simpler to figure out what happens there. So let's create sample 21. Just copy this stuff there. So then we can do this. And we can take a look at how it will look now. Actually, since I'm not using the slow test now, I will just do one quick thing. I will temporarily switch this off. So I can do stuff a bit faster. Okay, let's try it again. It should work way faster now in terms of showing us stuff. Okay, we got something. So we got like so for each allergen we have those matches, right? So it can be in either one of those. Fish can be either those as QGHC, as BZZF, or M thingy. Diary. Oh, I think I start to see the pattern here, right? Because for each of those, we also need to figure out the how many times they happen and how many mentions they actually have in which lines. Because let's try to prove that one of those cannot possibly contain any of the allergens. So for example, this thing, KFCDS, sorry, it can be in principle either fish or dairy, right? We have like indications in lines it contains, but it only is contained on the first line. So we have one entrance for this. And for this thing, well, that, I think ingredients to allergens is not very useful, right? At least not for now. So like the first one is the only one we need. So we have two possible things for that. Only one of them can be true at a time. And this thing is only used in one line. Okay, I don't see contradiction yet. Let's try to look at another one. So this thing can be also diary of fish because it's in the first line. What things? But like a lot of things can be diary. Okay, I feel that will take some time, so I will sit down. That will look funny. So let's try to figure out what is happening there. I'm trying to figure out how do we know that this thing... Do we need to also keep track of lines, of line numbers? Let's also keep track of line numbers, because I think maybe that will give us additional insight. So here, list. Let's add line number tracking. How many times do any of those ingredients appear? Insert. So okay, allergens to ingredients, we can then insert here this thing. But then it kind of destroys the purpose, right? This, let's just do it and see what happens. So, because then we will have like multiple entries, right? For each of those. But we will have, okay, I think actually there is something there. So if you try to look again, let's look again at QFCDS thingy. So it's fish or diary. Oh, okay. So that's kind of it makes it exclusive, right? It means that it can be either fish or diary, but not both. Well, actually, yes, that's true because it's like one word, so it cannot be both. Can one ingredient contain more than one allergen? They don't say. Which allergens? Okay, there is no mention if it can contain more than one, but I would imagine that it probably doesn't. So that's this key F thingy, right? And then for dairy, it's present here in the first line, and it's present for fish also on the same line. Let's look at maybe, instead of looking at the words, let's look at allergens. So dairy is on line 04, possibly an HM. Okay, a lot of them contain it. Maybe it will be better if we regroup it a bit. If we start to put in it, so like for each of ingredients, we will put allergens together with the indices. So it will be like hash map to hash map then. And here we can do the same. So we will have like allergen to ingredients to a vector of lines. Let's do it because I think it will also make it a bit easier to read. We insert ingredient index. But then it will override stuff, right? Oh well, entry for entry. So this will be then an empty vector, right? Here then it will be a push thing. Okay. Whoa. And here, let's do the same. Okay. And we can push to the vector, right? I think. hash map entry. Of course, or insert vector. Okay, that becomes interesting. Let's try to run it again and see what it gives us. Okay, it's definitely more readable. So we have fish match with this NHMS. Have soy, that can be either of those. So if I think about it, no, not here. Let me quickly clear it and run it again so we don't have, yeah, so this thing is probably an allergen, right? So it can be as a fish on lines 0, 3, or it can be soy on line 2, or it can be dairy on line 0. Dairy, fish, or soy. Line 2. Then soy can be either that or it can be this. If you look for this, this can either be a dairy or it can be a soy. Let's put the stuff that we got from the list itself also here for comparison. I'll just make them all this. Maybe those things we can intersect as sets. So if I try to intersect things for example, Kiev, CD, blah, 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 it can be dairy of fish at line 0. Can be dairy here. Fish here. This will just give me 0. If I try to intersect all for dairy, we will see oh, I start to see it. Oh my god. So dairy is mentioned in 2 lines. It's 0 and 2, which means that this is the only possible answer. We know that this is dairy because it needs to be in both lines, I guess. And this is the only word that is in both lines. But that is also true about fish. No, fish, it can be SQGC, blah, 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 because this we already excluded for dairy. If we would have tried to assume that this is dairy, that would not be fish, right? Then we excluded this MX thingy and we excluded SQ thingy. Now we need to see what else do we have. SQ. Then we have NHMS, which is, it says dairy fish, but it can be neither. So NHMS is not, Oh, I start to see it. So this thing then is not an allergen because both dairy and fish were excluded already. Whoa. So that sounds pretty nice. It's like when you look at the data, it makes way more sense immediately how to try to solve it. I guess that's one thing. Then SBZFF thingy. Well, same that it can be as dairy fish. We know that it's neither. In TRH can be as dairy, but it's not. And about soy, we don't know anything about those because we have only one entry of that. Which means, so first step would be can we just get like maximum length lists for each ingredient and print them? Let's do that. Let's try to do it like a bit more interactively this time, saying for each allergen. Where we will have then something like that. Max by key. So that returns lines, length, I guess. Can it return multiples? Because I think it will return only the first one. Let's order by key instead. Lines, length. We need to start with the largest one, so let's just also reverse it. And then we can collect. So this is like top ingredients. Oh, there is no order. Ah, yeah, we need to collect this stuff. I forgot. Shall we collect this stuff? Maybe we can do like cloned and then do like sort. Okay, let's do this. Kinda removes the purpose of having a hash map there, right? Because we go through all of those. Those are allergens to ingredients. So it's the first one. That's stuff I don't care about anymore. Allergens to ingredients, fish. Yeah. Well, I will just collect it into a vector then for now. Then toppings sort. Yeah, sort by key. Where we can do this, and then we can do yeah, this. Let's just do that. Let's first debug it and see what we get. Yeah, we also need, let's put allergen here. So let's do it like that. Oh yeah, we also need to reverse it. Or we can just actually do this. We can do it minus something. A. Ah, it's unsigned. Actually, so for each top matches R. This is like this thing. For dairy. Then for fish, those two. Those are the only ones we care about, right? Would have been nice to have group by, but I think it's not included in standard library. We can try to iter tools. Actually, yeah, you know what? Let's try iter tools because this is essentially kind of like standard library. Because I don't want to also spend so much time on trying to implement this stuff. Let's compile it and see, because I think it has it order something? No. Oh, so it allows you to do sorted by on iterator. Okay. Oh yeah, group by. Okay, I see. So, well, we got this, which is nice. Because then we can remove the whole additional thing, right? We can try to do it here. So let's try again. We need to use this thing. So here then, yeah, parse we don't care about. Oh, and also sorted by. So hash map. Savita, the sorted by key. We can just do rev, and then we can do group by, and we can group them by. Actually, we can even map them, right? We can create like those 3 tuples. We'll have ingredient, we have lines, and instead we'll have ingredient lines and lines length. So then when we sort it by key, so we like lines length, we just sort by this thing, and then we revert that, and then we just group it by line length. Which will give us what? So we get this, we get like key ungrouped. Well, I will just first collect it, right? And then we'll see what it gets us. So let's collect it into a vector. Line length. Oh. It implements into iterator. Ah, okay. Borrow from this file. What doesn't it like? And if I say into iter, okay. Can we do this? Then this. This is group by use size verse into iter string vector use size blah 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 use size. I don't see a problem. It It's iterable only by reference. Okay. Well, still doesn't help. What the hell? Should I do it here? Oh god, it feels that this thing is only more confusing now. Can I then, I don't know. Honestly, then this library doesn't make much sense because that's literally the only method I care about. And using it doesn't seem to be nice. Like this sorted by stuff. Know what? I don't care. I will do it myself. It seems easier. Okay. Top in this stuff has a vector. Let's just clone it for simplicity. Of course. Yeah, it needs to do something else, I guess. So this is like a hash map. No, I think I can just do it here. So we sorted them and then we just do fold, I guess. Do we have something like fold? No, we can just do a normal loop. So max group. What will it be? Well, we can do pop. We can do some. Can we do this? It must be attached to individual bits and sure. So we get this for top inks iter topping length. What is this thing? Is like string vector. Okay. So this will be ingredient that we don't care about, and this will be lines. If lines, let's do max group. What is the type of this thing? Vector is size. Yeah, I can take this. So this is like max group. That will be ingredient lines. Let's do this. So what we need to create from this thing will be top inks. Pop will be filtered, which will be just like a vector. Make it mutable. And then if lines length less than max lines, we break from the loop. Otherwise, we push. Found reference. Push this stuff there. distance lines. So this thing is now a vector of too many references. Let's do a bit of dereferencing here. I wonder if I can do this. It will annoy me with move things. So we do that. Let's remove double reference at least. So now we just got a vector of references to strings references to vectors of lines, line indices. We can already do this. And we should start seeing something, right? We can also remove filter tools. Didn't need them in the end. API was a bit confusing, so doesn't look correct to me. So for soy that is correct. Then we get this. But somehow for dairy we end up with the same stuff. If let's do this. Of course. Oh. How does it happen? Removes the last element. Okay. We don't need minus if you use pop. Makes sense. Okay. Now it should work. So for soy we got those. For fish we got this. For dairy we got this. And then do we report? Okay, I think we can remove this stuff. Let's remove those to not confuse ourselves. Try again. Oh, okay, now it looks correct. So we got for soy this, we got for dairy this, and we got for fish this. Less or equal to, of course. Not easy to group by hand. Okay. The hell? Why do we get only one? So if lines is... no. If lines are less than max line length, we break. Otherwise we push. Let's verify again that we are doing something that makes sense. So soy, those two. Top ingredients. Last one is, this is for dairy. Okay, this looks correct. We got top ingredients for fish, where we also got this in. I think, so for fish we are missing the SQ thing. Why do we miss SQ thing? So we pop MX. Let's print this to see what we get. We probably also need to print our allergen, right? So let's print this in. Gosh, it would have been just literally group by in Python or in Elixir. So for each allergen, top match. So allergen is soy, ink is this, and then let's go. Top ingredients. Pop top ingredients iter. We need to iterate from backwards, right? Because we're using pop. So here will be reverse. Okay, let's hope. Dairy. Yeah, it works. For fish, we got both of those. Okay, splendid. And for, okay. So now we can remove those additional things because we won't need them. We debugged the algorithm. And let's just do a bit nicer printing here. So then for something like that. So for allergen top inks filter. Let's just do that as well. Oh, let's not do that. Let's just rename the thing so avoid the confusion. My inks. Mentions that will be inks sorted by mentions. Top inks by mentions. So, okay, that's a bit more. What don't you like? Yeah, we need to do, of course, debug thing here. So now let's try it and see if we will achieve higher enlightenment with this kind of output. Oh, it even doesn't require additional spaces. Sweet. So for dairy, we got this. For fish, we got this. And for soy, we got this. Shall we try to see what our output for actual task will give us? Maybe we will already start to get some better idea of what we are dealing with. So I will do this. Oh man, I think I can even by hand now to map it, right? For soy, for shellfish. So how many times do any of those ingredients appear? So essentially, what do we need to do now? We found for each of the allergens, we found the top ingredient that is mentioned in more lines than any other one. We also got those vectors of lines where they are mentioned, which looks almost like, actually that's maybe a thing on which we also need to line intersections. I'm not sure. QMRPS. So yeah, let's switch a bit back to our sample input. But this is like manageable. I think we can even partially at least figure it out by hand. Which is, by the way, not a cheating thing in Advent of Code, because in some tasks, it's really impractical to try to automate it. For example, when you get like OCR kind of stuff, though people still do. So we got this stuff for dairy, for fish, for soy. So let me copy it and quickly pre-process it a bit. And also say this. Let's print this now and look at those two things together. I want to compress those a bit because otherwise they're not readable. So let's infer stuff. So for fish and for dairy, we got this. So stop for both fish and dairy. The only top for dairy. Okay. Then actually we can also check mentions, right? 0 and 1 is dairy. And well, actually for dairy we know the only top for dairy is the only top for dairy is I think that's how it works, right? Then for fish we have mxmxvkt and sqghc. mxq and is dairy. So, oh god, what was that actually? Oh, it's like breadcrumbs. I didn't want. Yeah, let's toggle them back. Okay, so is dairy and then mean sqghc is the only choice for fish. For soy, FVGKL is the only choice, since for soy we have and Ooh, that starts to look a lot like topological sorting to me. Is, yeah, so we have this and is fish. So this is for soy. So now let's also, what else do we have? So this we selected, this we didn't select, this we selected, this we didn't select, and this we didn't select, this we selected. And those are, yay! I think we kind of solved at least the sample input, because those are exactly the ingredients we need for that we know that can't possibly contain any of the agents in any food for your list. And then for all of them, we can take those. We already have lines here, right? So we can just, that we can put into a hash set. And that we can put into a hash set. So this thing, 0, 1, 0 in both of those. And here we got 1 and 3. So we got 5. So I will put it here so that we have it as reference, and then we can convert it into a nice stock comment, right? So that's the power of interactive programming, by the way. Just by looking at data and playing with that, we got quite long. And of course, in Rust, we don't have interpreter, but at least we have the tests. So that's how we substitute. Not a perfect substitution, but at least something. So how do we figure it out? Well, we do a very simple implementation of topological sorting, I guess. It to be to contain that allergen. If we so this is like, I'm not sure that this is absolutely correct, but I think it's close to that. Actually, it reminds me about some mathematical thing about pigeons. Let me quickly Google it because maybe I remember it. Pigeon theorem. I was thinking about this thing. If n items are put into m containers with n larger than m, then at least one container must contain more than one item. So yeah, it's kind of like with the allergens ingredients. For example, if you have 3 gloves, then you must have at least 2 right-hand gloves, or at least 2 left-hand gloves, because you have 3 objects but only 2 categories of handedness to put them into. Can be used to demonstrate possible. For example, if you know that the population of London is greater than the maximum number of hairs, they can be present on a human head, then the pigeonhole principle requires that there must be at least 2 people in London who have the same number of hairs on their heads. That's pretty cool stuff. Cup plus. Okay, let's not get too into that, but I think it's kind of related to that, not sure. So, for each can we actually do it with like top dimensions contains that is not conflicted by other dimensions, top ingredients. So we should always have like this choice, right? If we look at this stuff. So for dairy, we have only one ingredient. So that's what we know, that why we know that mx blah 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 is the one. About ingredients, top ingredients. We can use topological sorting to out the allergens where the choice top ingredient is determined. Can we actually do this on our input for the task? Let's check it. Nuts. And if I try to do it by hand, nuts, shellfish, yeah, I guess it should be topologically sortable, I think. Can I actually sort it topologically by hand? Let's try it. So we can refine it as well, right? We can also say if we have, like, if we won't get correct answers, then one thing to do, consider matches between lines. Maybe we will get like different lines, you know, stuff like that. But I think it won't happen. I think it will be a bit too complex then, so I guess this should be that. So for nuts, let's do nuts. So we can then just remove it. We know, by the way, that all those entries are same length, right? Because that's one of the things, it's like by construction. We got that. Getting like proper mathematical proof, of course, will be a bit tougher, but what can you do? So we got nuts that. Then we get shellfish this. So now we got only one option for wheat, which is this. Oh, and here, no, for dairy we got this. Yeah, it's topologically sortable. Gosh. I think topological sorting is the algorithm that I wrote more than any other algorithm in my career. It's one of the most useful things for sure. And I think I should do a proper video about it because I think a lot of people don't know it, but it's actually one of the most useful, most broadly useful algorithms ever. And then, of course, fish is this stuff. X is this stuff. Well, peanuts and soy. So we figured it out, but now we need to make computer figure it out. Or actually, should I just put this in here and then, yeah, you know what? Let's just say, do proper topological sorting. So we got this. What do we need to do next? We just need to we could just then take the ingredients to allergens. We can then just take allergens to ingredients. We can take the second hash map, I guess, and just count the appearances, right? Ingredients to allergens. So let's remove the things that are not ingredients. This would be like allergens. Allergens to lines. Shouldn't be in known allergens. So that's our thing here. Let's do a vector. lines. We can then do like, we can take this, we can then do like iter into iter, and then we can do like map, we can do like x, we can do to string, then we can collect it to a vector just for fun. So we got a vector of strength e. Oh wow, I guess it doesn't work because we have like next line, which is oh, actually, so contains ingredient. So we only take those who don't, and then we map them again. We have those maps now. We only care about lines, right? So we just take this stuff. Origin to lines. We convert them to what? We take, we map them to origin line. We collect it into a hash set of lines. And then we just return length, and then we collect this stuff to a vector. Well, we actually can do count, but let's try to see if we got everything correct. So map into iter map line. Okay. Of course, that should be a tuple. Oh man. I guess we can do it like that. Okay, and here then it should be a vector of numbers, but let's do count. Oh, sorry, sum. So mentions let's extract it just for beauty of that. I know that we don't necessarily need to collect here, but I want to. non-allergic to lines. Actually, that's what I want to do. Line, we get line, we collect it to a hash set. Actually, why not? Oh, we can collect a hash map vector, sure. Oh, we can just map still. And here, of course, we need to iterate. And here, finally, we can do some box new, and we can put mentions non-allergic. Okay, let's see if that worked. We can try it in our REPL. And if it works, we then can try it in our proper task input. Quite excited about this stuff. This task was very interesting because it's kind of, I think I figured it out, but it's also something that I wouldn't be able to immediately replicate without looking at data again, right? So let's start with sample 21. Oh, sum 12. Why? That's, by the way, good things that I did this, because now I can look at this stuff. Oh, okay, see. So allergic to lines, it's like a vector, and then we need to flatten, of course. Okay, so if we flatten now, it's 13. We got too many things here. We got, oh yeah, because of course, well, we can just put this stuff there, right? mx, we don't have it in our input. So this is like sample. Let's do it like that. Of course, actual test input. And this is like sample input. Ugly, but what can you do? I'm too lazy to implement topological sorting right now, so. Oh, we can still do it, I guess, after verifying that we solved the task. But first I want to try to see that. So cd blah, blah, blah. Cd blah, blah, blah. Physical. Those are, well, actual test input, sample input. Okay, that's better. So we can try it again and see. Five. Okay. And it gave us, for the task itself, it gave us this answer, 2000. Okay, let's try it. Not sure if it's... Whoa, we solved it. Okay. That went better than I expected. Let's see what part 2 asks of us. As a inert, you should have enough information to figure out which ingredients contain which allergens. In the above example, contains dairy, contains fish. So this is like topological sorting, right? Alphabetically by the allergen and separate them by commas to produce a canonical dangerous ingredient list. Any spaces in a canonical dangerous ingredient. In the above examples, this would be so dairy, fish, soy. Spread them by commas alphabetically by their allergen. In the above examples, this would be blah, blah, blah. Time to stock your raft with supplies. What is your canonical dangerous ingredient list? Oh, wow. It's the first time I think we have a string that we need to enter. So yeah, let's quickly codify stuff that we just did. I think I'm a bit too wasted today for day 20. I will do a quick review after solving the second part of the task and for day 21, and I will tell you how far I progressed. I solved the part 1, but I'm still struggling with part 2 of day 20. I think it was the most complex day so far. But I also was not kind to myself because I tried to solve it via mean conflicts, which is not the easiest way to solve it, to say the least. So, the allergen. Actually, I think I can already just do it by hand, right? So we got well, what can you do? That input. Just in case, dairy. Let's reformat it a bit nicer. So, I guess I can remove the space just for simplicity, and then I can do split by, no, actually, let's put it like that. Input, I will just redefine it as a hash map. So split by that. And then actually I can also do this because I can then just stream white spaces, right? Those like our pairs. Then I can say, oh yeah, I cannot collect into a map again. Well, I can just actually, I don't need to, I can put it into a vector and then I can do sort by. So, that's good. You can take the pair and pair with split by this thing. And then we just say so first thing is the allergen. The next thing is ingredient. And we just do allergen ingredient. And then it should be mutable. We got pairs. Yeah, we can also do trim on those just in case. To remove the white space, and we got this stuff. And then the only thing we need to do, input, let's call it like allergens to ingredients. So we need to sort them by the allergen. Sort by key. Just in case, let's verify that we are not doing something dumb. And then we just need to concat stuff, right? So here we can do for struct, yeah, collect into a vector, of course. Sort by key. Let's make them both strings so that it's a bit simpler. Must outlive tool. Come on. This is a vector of strings to strings. We sort them by key, takes reference to self, mutable reference to this thing. Sort by key. Allergen. Well, let's copy stuff. So we got this, and then what do? We just go through that and we learn this, right? So allergens to ingredient, map. We don't care about allergen, we now care about ingredient. We do ingredient, and then we collect into refactor, I guess, and then we just join, and we join them with just commas. So this is our answer. Now, one problem that we will have that I guess my magic, into just iter. Let's do into iter. Let's consume. It doesn't matter at this point. What don't you like? Yeah, debug moved it, so we can go back. I guess that's the thing. Let's run it and see how it goes. Oh wow, it worked, but of course we did something dumb. We need to trim it here, but I think I can, for now, just manually do this. So I can take this stuff. Ooh, it takes fish. Shellfish. So... PS, QNVX, QG, CLG, VG. Yeah, it didn't parse this one. I can do it like that. Now I think it should work. Oh, yeah, of course. Sorry. So we solved day 21. Okay, that was way simpler than day 20. Shall we try to code quickly the topological sorting? Because that was the thing that I kind of just like inferred by hand. I think we should do that quickly, and then we can look at day 20. I won't attempt to solve it today because I'm a bit tired for that, but I will tell you how I solved the part 1. And I will tell you how I plan to solve part 2, but I will guess I will do it not on stream. I will be back on Wednesday as well. So on Wednesday, I hope to stream days 22 and 23. And on Friday, we will have Christmas. So I think I should have enough time to stream, but maybe I will do it after the Christmas. We will see how it goes. It depends on family plans a bit and stuff like that. But yeah, so topological sorting. Now, this algorithm I will just look up because though I wrote it multiple times, I wrote it always in functional style. I think in Rust it would be easier to do topological sorting in imperative style. So empty list will contain the sorted element, set of all nodes with no incoming edges. Well, S is not empty, do remove a node n from S. Yeah, by the way. Let's commit this stuff. So while set of all nodes with no incoming edges, while set is not empty, remove a node from S at n to L. For each node n with an edge, if from n to m, do remove edge from the graph. If m has no other incoming edge, then insert m into S. Graph has edges, then return error, else return L. Now graphs are typically, the easiest way to represent graphs is again with hash maps. Hash maps fun, no surprise here. And we're already using them quite a bit Here we don't need to go. This is the typical algorithm-based way I also implement functional just without mutability with recursion. Here we will, I think it will be even actually shorter to just do it with a loop. I kind of start to like again imperative programming because of all the Rust stuff that I did this year. It is not as awful nowadays. I think I kind of started to enjoy it as well a bit more. So this is like top match, and then we get here. So we need to known allergen ingredients, right? So let's do with no incoming edges. So no only choice. Let's do it like that. So this is like only choice for some allergen. We go allergen. Oh, we still need to build the data structure, by the way. So that top choices. No, it's very mouthful, but this is all right. This will be then hash map. It will be new and it will be mutable. So here we can do insert. We insert allergen, top ingredients by mentions. This is all right. So this is insert this thing. And values then will be its top ingredients by mentions, which now contains vector of lines that we don't care about. Top ingredients. So then will be two mentions, by mentions, two mentions. And we just go through that. So we do into iter, we don't care about that anymore. We map it, we get like ingredient. And then we get like mentions that we don't care about. So we take ingredient. Ingredient will be this thing. To string. And we collect it. We collect it into a hash set, I guess. And this is our top ingredients. Right? Splendid. So we got this data structure now, and it maps every allergen to its top ingredients by mentions. Those are like our candidates. And here we can just take it and we can say find. So like do iter find allergen. So we'll have allergen that is then mapped to its ingredients, possible ingredients. So you'll have only choice. Oh yeah, we will still need to remember allergens as well. So we'll have allergen and we will have candidate ingredients. And then candidate ingredients lengths should be equal to 1. That's our initial assignment, right? So we can say, let's check it out. It's always easier to work when you see what you're working with. So here, thankfully, Rust has this amazing macro debug that I use all the time, as you may have noticed during Advent of Code especially, because you have so many data structures that you need to keep track of in some tasks. When you see stuff visually, it's way simpler to work with that. So we got a bunch of things here. Blah, blah, blah. Oh man, I think we need to stop printing something. Yeah, let's not do this. Let's try it again. Nuts. Yeah, that's exactly what I also found by hand, so you can see that we are doing something correct. But here I got, yeah, it's hash set, that's why. And this is the data structure that we have. Allergen to top ingredient by mention. You can see that, yeah, we got nuts, and then we can figure out that wheat is that, etc., etc. Actually, I guess I don't even need to implement like the whole thing here. I can just go and modify stuff. Oh, wow. Yeah, true. So let's just say known. We need to build this, right? Allergen to ingredients. Yes. So we will need it later on. So we can just build it here. We do like, so this will be still hash map. We don't even need the whole topological source for that. That's so funny. And then we just go while let sum, because this is allergen ingredient. Let's go to one ingredient set equals to this expression. Oh, but that is this thing should be mutable, right? Set. Can I make it mutable? It's already mutable here. Well, the ingredients by mentions. And I don't need it afterwards, right? No, I don't need it afterwards. So I can destroy it. Some urgent ingredients by mentions. Well, we can do this. Stop. Urgent ingredients by mentions. Can I call remove here? I think so. Yes. One ingredient set. So hash allergen to ingredients. We insert allergen to string and ingredient. Is it set first? Can I pop? Does it understand that we are working with a set? Let me quickly check it out. Let's do this, I don't know. So, expected one, sure. Don't remember. I think it has like pop, no, remove value, remove entry, take one, I guess. Well, I can also just collect it vector, I guess, but let's quickly check. So hash set. Reserve, retain, shrink, take, iter, drain. Well, drain. Get. Shrink, take. Take, I think, take will return me an iterator. Oh yeah, I can just do, I don't need to, I can do take and say 1. That is equal to the given one. Oh god, okay, that doesn't make sense. Well, but then I can also do first and just do unwrap, I don't know. Let ingredient, right? No, it doesn't know first. For struct. Oh god. Take 1. Yes, take 1 and do next then on that and unwrap. Satisfied? Satisfied. Splendid. To string. Cannot borrow because it also borrow as immutable. Of course it is. Ingredients by mentions. Cannot I like put it into a different thing? Do we have any mutable borrow here? Let's quickly compile and see. Immutable borrow occurs here. Can I make it non-borrow? Okay, no. Let's I think it's just confused. Only choice. Well, not as nice, but what can you do? Only choice. Oh, it still doesn't like it. Dimensions. Well, I cloned this thing. Find. Ah, okay, okay, that works, I guess. Okay, after some little scuffle with the borrow checker, we figured it out. So I'm just cloning this thing. Oh, but if... Ah, yeah, I'm cloning it, but here I'm removing stuff. So this should actually arrive at this thing. Let's do that. So let's do allergen to ingredients to check. Let's try to see it again. Allergens to ingredients. Oh, and by the way, we didn't need this all two ingredients here. Oh, we need it. But that we don't need. Okay. I think I'm still doing something wrong here. Is it like always cloned? Dairy, eggs, fish. Ah, okay, so we solve it. And then dimensions. Dimensions. I guess let's remove the sample stuff for now and make it run this. The top ingredients by mentions, allergen. So it doesn't compute stuff. What? We are doing correct thing. Top ingredients by mentions. Can I do like another thing here? I will do like dimensions temp. So this is like my clone. And here doesn't work. Can I do like, maybe I can just replace it. See if I do like clone and I remove or no. I guess we have no choice but do this like only choice thing. Okay, that didn't work out as well as I hoped. But what can you do? So this is our only choice, and then we can do... Let's just do allergens to ingredients by mentions. Only choice. To ingredients, and then remove allergen. Come on. It contains some kind of reference. Can we do like clone on that? Cloned. I really need not to have reference here. Now it doesn't like me. But I can, oh yeah, I can map inside option, right? So we got what? We got this, stop. We got this only choice being an option of string and hash set. And we can then map here. So that is allergen, one ingredient set. And here we can do then that was the problem actually, I guess. Ingredient set, allergen ingredient. Allergen we can convert to string, and ingredient can convert to string too. Here we can then do this. Moved value. Sure. So move of course because sure. No. But actually I don't mind. I'm like alright with moving this stuff out. Well, I can also do references here. Shared reference. Gosh. Yeah, today is borrow checker day, I guess. Satisfied, finally. Can I do now only choice here? Well, that will look very ugly. What can you do? Yay. It's better, of course, to make it into a proper function, but so far I just want to check that it works. Did I do it correctly? I'm so confused right now. So, no, I didn't. Okay. I guess I really need to start making a function, right? So, talking about mutability, allergen to ingredients. To ingredients. It's German. Get allergen to ingredients. That returns a hash map. Allergen to ingredients from string to string. Hash map string to hash set of string is called allergens to top ingredients by mention. It's hash map mapping string to hash set string. The top ingredients by mention, we got this. We will do, actually we end up with pretty much functional solution here. That what can you do? Ingredients by mention, and we got allergen to ingredients, which is hash map, our answer, and eventually we return this, so recursion. So we pass this magical beauty allergen to ingredients by mention, actually allergen to ingredients, that's the thing here, right? This will be a reference to the thing, we just clone it here. So two ingredients inner. Okay. And now agent top ingredients, we iterate, we find, we map, we got only choice. And then we match only choice if it is some this. Let's do that. Allergen to ingredients is this thing. Just pass a mutable reference to it. Here then. Here we got some mutability going on. Into this, and then so if that happens, do this, makes sense. And then actually I can also create here clone. So we clone this stuff and let's reorder it to match the order of arguments. And here we will send a mutable reference to it. And here we will have a mutable theme. Top ingredients by mention. Will it work now? Mentions remove, and then we do get allergen to ingredients inner, where we call ourselves recursively with this stuff. And if it's none, we just return. Okay, finally. I can even do to make it a bit shorter. And now I really hope that this will finally work. Let's see. This scene breaks my mind. Sure. You know what? I will run it from here because I think it's a bit easier. So we start with the stuff. We get nuts. Allergen to ingredient. It feels to me like we are not really removing stuff. But how can it be? Group ingredients by mention. Ingredients inner mentions. We got immutable reference to a hash map. We then remove we remove allergen, but we don't. Oh, hey Thomas. Yeah, I did day 21 semi-manually already. Now I'm just implementing topological sort because it's required to solve it. But yeah, day 20 will be hell, I warn you. I solved the first part, but not the second part. I guess I will do it after the stream because I'm a bit mindfucked already. So, but yeah, I guess I did. So we pass those references here. The immutable mutation works. We remove this stuff. It also works, I guess. But then we also need to go through to top ingredients by mentions. All the fun. Iter. Can I do it? For what this thing contains? It's a hash, so it's like allergen, and it contains a hash set. I actually can do iter mute, right? So ingredients, candidate ingredients. Yay. In stuff. Yeah, this is mutable reference to a hash set, so we can do remove and remove the ingredient. What doesn't it like? Expected, sure. Now it says it moved. Yes, sure, it's moved. Let's clone. Why not? Actually, we can also just do this to avoid cloning it again. Right? We can just reorder them. Yeah, we can reorder them. And then this clone won't be necessary because this is, yeah, and allergen is also, by the way, string. So I guess I can remove both clones here, which is nicer. I think that's it. Let's try again. So. Yay. We got it. Nice. So now I don't need the bug printing here anymore. And let's quickly compare it with my hand figured out thing. Nuts, Q, arm, gears, shellfish, Q, and VX. Splendid, we solved it. Okay, well, we already solved it before. We just solved it with computer now. Sometimes computers are not completely as agents. We can use topological to figure out. We can use topological sorting to figure out. Let's choose one top ingredient. So it's like algorithm. Okay. No allergen ingredients. just map it to, so we ignore allergen, we only need ingredient, we just do like ingredient. Can we actually leave this having references here? I think we can. Seems so. So now we can also uncomment and make sure that we have both things running for part 1. Then it's like puzzle. Yeah. Puzzle. It is nice until you, like, it looks easy until you calculate the number of options you need to consider. So combinatorics is usually makes it harder. But you can always, another solution that is valid would be to 3D print those puzzle pieces and then move them around until you figure it out by yourself. So also an option, I guess. Yeah, we solved this stuff. And by the way, we still need to write the test for part 2, right? So let's just do it with input, I guess. So 21 part 2, what was our, yes, that's the solution. Let's put it in our test. And then do quick refactoring to make sure, yep. And that should be string, of course, to string. Yeah. Option boxed U60 something. Oh, I'm in the wrong file. Damn. Okay, sorry about that. So let's go back to the right file. Yeah. Here. So solution is this. We do a string from that thing, and then we can do assert solve to input some box new solution. I can do it like that. That's nice, I guess. Okay. Now we just need to do quick refactor, right? I think, by the way, with like list of items thing, I didn't really need any of that. Much as so that I can also remove that we don't need to consider, thankfully. Non-allergic to lines. So now I want to do a bit of renaming to make it also a bit more maintainable. Not sure about the sentence. Tiles at the end of the image also have this border, but the outermost edges won't line up with any other tiles. This don't need to. Yeah, it means don't need to. And this is super important for figuring out solution without breaking your mind. So I will not spoil further. But yeah, it just means don't need to. Allergen to integer. Allergen to ingredient. So let's replace ingredient to allergen. So now entry. Yeah, exactly. Those are independent essentially. In principle, then it means like it's 12 by 12, I think, 144. So it's like factorial of 144 multiplied by the number of rotations, which rotations and flips, which is 12 for each of those, I think. Like 144 factorial is only like arrangements, right? Though they can be, it's also actually divided by 4, I guess, because of symmetry. But yeah, something like that. Very big number. allergens list. So we start with creating those things, allergen to ingredient, ingredient. Oh, and by the way, they are not even correct, right? Because allergen to ingredient, to ingredient with lines. I know those names look super ugly, but imagine looking at this thing like 2 months later. That will not make any sense. So it's better to have like really long name. Yeah. How did you solve part 1 for day 19 if you only need to change one line? Did you solve it in Haskell? People were memeing that if you solve it in Haskell, then it's lazy already, so it kind of solves it automatically if you solve the part 1. Ingredient with lines. So this stuff we have ingredients of lines. Can we continue to contain that top choices don't contain such in question since they cannot cover all the appearances of the arch. So let's extract this magical function now. Let's do some extraction to make it just nicer. We solved task already, we're just doing it to make our life, to make the solution look a bit nicer. That's the only reason really. Ah, okay. But you also converted it to regex in day 19, just like creating a regex from the string. Because in my case, I actually checked stuff like for matching things. I had like 3 regexes and then I counted appearances of smaller regexes to make sure that numbers match. Hash maps with lines, with line sets. So that magical thing will return us this stuff. Hash map string vector. So let's just copy that. Actually, no, I think extracting this function will make it even less clear, right? So it's better to extract from here. Oh, wow. So, okay, I decided that I'm not ready to build non-deterministic automata myself. And Rust already, the guy who wrote regex already did it. But I think that's, of course, fancier solution, right? It's way more interesting. I looked it up. I thought maybe I should try, but in the end I decided that it's too much effort. Top ingredient by mention. So that's the thing then. I think you wrote your thesis about this stuff, right? I looked it up and there was something about automata, but it was too mind-breaking for me to get too deep into. So what are we building here? We're building this magical allergen to top ingredients by mention. So get allergen to top to groups of top. Yeah. Mentions. And we just do this and we just will return this in. So it starts to, compiler will tell us what type to write. Yeah, it needs this argent ingredient with lines, which is the ingredient with lines. Can I? Yeah, I can insert explicit type. Yay. That is always nice. Which should be hash map string vector usize. And we also use this. So all ingredients. And now quick fix. Oh wow, that sounds really crazy. Alternative set theories that would allow for recursive sets. Wow. Okay, mind breaking it is. Get argent. Okay, so that stuff we can now write. Top ingredient match for each argent. Only one of those ingredients can be guaranteed to contain that argent. Let's make it like official comment for the function. Map from allergen to a hash set of possible containing it. So, and now we can replace this thing here. So this thing doesn't need to be mutable anymore. So that also goes to become a comment here. Add line top ingredients by mention. It's essentially sortable. Actually, yeah, that's the pipeline. So we did that, we did this. Now, okay, I think get argent to ingredient. With lines. Get argent to ingredients. Right? Yes, I think so. So that thing. Oh, that's actually quite long. But it's mostly, like most of the length really is because we didn't have group by. Argent to... Then this is very specific. get allergen ingredients by mention. So actually, when I'm looking at the structure now, I can see that this stuff is only used here. So I can move this call here. Allergen to ingredient. And then this will be allergen to ingredient with lines. And then this will be that. Let's extract the type. Ingredient with lines, right? Oh, we forgot, I guess, one. Of course, it's need here. It needs a specific lifetime. Right? So get allergen to ingredients. So this stuff becomes just a helper function here. Nothing super fancy. We can move this huge mass of code a bit down. And here, so that stuff we don't need to care about here. We only need this thing. Okay, splendid. So now we still need to actually extract this as a function, right? Lines. Yes. Okay, let's extract it. So actually, do we care about list after this point? No, we don't. So our parser can return this stuff. So then our parser returns both of those things. And another one, ingredient to allergen with lines, right? Ingredient to allergen with lines, which doesn't know yet, but we will teach it. So actually, I think it's the same, right? We just like switch the order, so it should be isomorphic, almost isomorphic. Collection string font struct hash map. Of course, here it doesn't return references; it returns ownership. Splendid. So then type list is never used. Type item, to be honest, oh, we can keep it here, doesn't hurt us either. Get allergen to top ingredients. Get allergen to ingredients inner. Actually, So splendid. And then our solution for the part 2 will be essentially ingredients to ingredient. And we can do mute here. Agent ingredient. Get agent ingredient. Gosh. Ingredient. Shmup. Sort by key. We need to convert it to vector, right? Into iter collect vector. Allergens to ingredient. So that looks to me like we solved it, and this stuff we don't need, so just ignore it. Something it doesn't like. Why don't you like? List. Oh, those things refer to list. That's why we have references, right? So we have like, well, we just do this, which will also make our type declaration a bit nicer. So this thing is rather typical way to refactor as programs. So you, like, if you have those complex types, you name them, you extract them, you then start to extract functions, and then stuff slowly becomes nicer, nicer, nicer. So here we can just give it also type declaration now, right? And we will see where we fail. So here, for example, it says found string. And this is allergen index. So now this thing doesn't like what we're doing. Okay, that we fixed. Now we can add here another thing. And we can see again, it says to us where we need to do toString. Where we need to do toString. And we are golden. I think we don't have more errors. Well, we still have errors, I guess, where we... No, we don't. Contains... well... hash set contains ingredient. We can just do this. And I guess top ingredient iter shared reference. Yeah, So, anything else broken? Doesn't seem so. Yeah, let's try to run tests. Yeah, one thing that I wanted to do still. So here we have ink. Let's give it better name, ingredient. Lines. Ingredient. So. Okay, I think it looks fine. We can run the test. We can commit our refactor, and then we can look at day 20 part 1. I won't be doing part 2 on the stream because I think it will be a bit too stressful, but I will show you how I got to part 1 solution at least. And also let's quickly check that our day 21 behaves in the REPL the way I want it to behave in the REPL. Splendid. So solution is quite fast, as you can see. Yeah, good idea. First off, I will show you how the REPL works for the first part of day 20. You can see that we got very quick solution, but now let's see what it took to actually get there. So, day 20. Yeah, so far I solved everything except the second part of that scene. So, but I'm sure I will solve it still. In essence, you get like images from a camera, but they are randomly turned, flipped horizontally or vertically, or rearranged. So you need to find a square arrangement of them such that they borders match. Yeah, about constraints, that seems to be a bad idea. I went with this thing, but it didn't work out that well for me. And I spent a lot of time trying to optimize it. Yeah, I will get into that in a second. So yeah, the camera appears to be malfunctioning. Each image tile has been rotated and flipped to a random orientation. So you get like tiles with like indices, with IDs for each. And then you need to figure out how to put them together so that they borders match. So for example, if you look here, you can see that we got this border, it matches with this one. Like right border here matches with left border here, etc. So essentially left, right, top and bottom borders should match with left, right, top and bottom neighbors borders that are opposite of that. Yeah, here. Top, bottom border of here, bottom neighbor, its top border matches with bottom border of the top neighbor. See you later. Then when you do it, you need to take the ref IDs from the corners and multiply them together, and that will be the answer. So since I really like constraint satisfaction stuff, I decided to try mean conflicts algorithm for that. And day 20. So first, of course, you need to parse stuff. Parsing stuff in this case was comparatively easy. Yeah, like input that you get is quite big. Sorry, that's input. So that's like a lot of lines. It actually ends up being 12 by 12 image, so 144 tiles. as you may guess, like if we try to brute force it, the number of permutations of 144 tiles will be factorial of 144. And we also got rotations and mirroring. So for each of those tiles, there are 4 possible rotations, 2 states of if it's flipped horizontally and 2 states if it's flipped vertically. So we got like 16 possible things to consider there. It's actually less. I think it's actually 12, if I remember correctly, because some of those are symmetric, so you end up with the same exact image. This whole thing is a known thing in mathematics. It's called dihedral group. So yeah. So yeah, the dihedral group is a group of symmetries of a regular polygon which includes rotations and reflections. So this is like essentially our task here. There is a bunch of things you can learn about group structure. You can represent it as matrix. This is a thing that is commonly used in computer graphics. In computer graphics, this thing is also known as affine transforms. So it's geometric transformations that preserves lines in parallelism. So moving to an angle and like reflections preserve those. So that's why they are affine transforms, and you can use affine maps, matrices, to do them. And that's how you typically do them in computer graphics when you, for example, build a computer game. Actually, this like affine transformations is one of the first things that you learn about when you start to study computer graphics, computer vision. But we have a bit more restrictive case. We just have like 4 possible rotations, and we have like 2 different directions for flipping stuff. And as they say, you can represent it as matrix. So first, before we even figure out the arrangement of tiles, we need to figure out how to rotate things and how to check if we actually found the solution. For that, I needed to parse input, which I did. It was quite simple. So parsing function is small. I will not stop on that much. It's pretty much like all other parsing functions here. You split, you push stuff to hash map. You get a hash map from U64 to a tile. Tile is a struct that has raw representation, which is just vector of those lines that we got from our input. And it has also a vector of edges. So this was a little optimization that I did. Essentially each edge, so like top line, right edge going from top to bottom, bottom edge going from left to right, and left edge going from top to bottom. They're stored in this edges thing, just as strings. In this vector always has 4 elements, and first is top, the second one is right, then it's bottoms and left, so going clockwise essentially. This is just for like optimization to not re-extract them every time, because we need those very often. Now we got the hash map, that's our puzzle input, and now we need to figure out the arrangements. We need to figure out how to rotate and how to rotate stuff and how to extract edges after rotations. So for that, I implemented an additional data structure that I call transform. So this transform is essentially this dihedral matrix, but it uses, it has 4 possible rotations that are expressed just as U size. So 0 is no rotation, 1 is 90 degrees left, 2 is 100 degrees rotation, and 3 is 270 degrees left rotation, which in this case means we are going counterclockwise. We also have 2 booleans for if it's flipped vertically or if it's flipped horizontally. Then for this thing, we have different implementations, right? We have some functions that allow us to work with that a bit nicer. So we can get, first of all, a vector of all transformations that we can apply to a tile. That will be important for finding a solution. Yeah, actually, in this case, we don't care about symmetry, so we can simplify our problem a bit by removing symmetric transformations, but we don't do it here. I just create like this vector with capacity 16, including the default transformation where we don't rotate and we don't flip anything, We go through possible rotations, we go through possible flips, we create transformation structs, we push them there. All nice and simple. Next thing is actually getting applying those transformations. So for that, I pretty much try to simulate this matrix. I try to simulate it with edge IDs and flip maps, where we essentially have an array for each edge. Remember, we have this edges vector in our tile struct. So here we are using it. Essentially, we have a vector of, we have an array with 4 elements. Each element corresponds to an edge, and each element is a tuple. A tuple that contains an ID of the edge that we should return after applying the transformations. So for example, if you have this transformation which does flipping from vertical flipping, what will happen? Well, if we ask for top edge, we instead need to return bottom edge. If we turn 90 degrees to the left, it means that our right edge becomes our top edge, and our bottom edge becomes our right edge. But bottom edge is now going in reverse order, because we always go for the right edge, we go from top to bottom. But if you turn 90 degrees to the left, counterclockwise, what happens? Bottom edge, it was before read from left to right, and now we need to read it essentially from right to left. So we need to reverse it. And that's why we also have another thing here. In each of those tuples, we have a boolean that expresses if we want to reverse chars. And then I just manually I drew it and I calculated for each possible rotation which edge will be where, and then if we need to reverse the characters. And that's essentially our matrix for rotating and flipping stuff around. This is only after applying rotation. Now, another thing that is important to know about dihedral group is that you can apply those operations independently from each other. So if you flip and then you rotate, or if you first rotate and then you flip, doesn't matter. It commutes. It will work the same. So I first rotate, then I flip. So flip here is very simple, right? If we know that when we flip horizontally, if we only need to essentially the top and bottom edges, they go into another direction now, which means I need to reverse the reverse character boolean, but keep the same edge there. And left and right they switch places. So that's what I do here. Alternatively, if we are not flipping horizontally, nothing happens. Then we do vertical flip. For vertical flip, we go from, essentially, we do similar thing but in reverse, right? So top and bottom, they change places. So that's what we do. First element is top, now it's bottom. Second element from our previous computation. Bottom becomes top, and left and right, they don't change, but they change the direction of characters. So we need to reverse them again. So that's why we have not reverse char boolean. And that essentially expresses what we need to do to get any edge we want properly. So then on our tile struct, we have this parse that returns us hash map, right? We also have top edge, right edge, bottom edge, and left edge methods. All of those, they're similar. I will show you 2 of those. Essentially, one is doing edge with ID and position, and it just pushes it calls a function, helper function edge with ID and position on itself, on the current tile, pushing the number of the edge there and the current transformation we want to apply. So those kind of return top edge or right edge or bottom edge or left edge after the transformation. And for right edge, we do the same, only now we do 1. For bottom edge, we do 2 because it's the index of the edge in the array of edges. And then we have 3. For edge with ID and position, then this helper, what it does, it takes the reference to tile, it takes edge ID, and it takes transformation. And then it calls this edge ID and flip map that we just discussed, that has those nice matrices for performing those operations from dihedral group. Oh my god, too much talking today. And then we just select the elements that corresponds to the edge ID we want. Then if reverse character is set to true, we reverse characters in the edges array element with edge ID we got from this transformation thing. Otherwise we don't. And we just clone them and return the strings that we got. So that's it. That's how you do flips and rotations. It took me some time to arrive at this nice abstraction for doing that, but I think now it looks super clean and smooth because that's essentially, this is the whole logic for that. This expresses this group, and then we just use a bunch of helper functions to provide nice interface on top of that. Now, these transformations be done, we need to be able to solve the task itself. And here where things got complicated. So as you can see, this file has 600 lines, and this is first part. In the end, most of the stuff that I wrote for trying to solve it, I didn't use, or like I used it kinda, tried to use it, but it didn't really work well. It works super well on the sample example, which is 3 by 3, so 9 tiles. But for 144, it just doesn't really work well. But then I found another heuristic solution that actually worked immediately. So first we start with parsing the tiles, and then we need to, in this case, what I ended up with doing, we count edge match counts. So we create a hash map from tile ID to edge nums. Gosh, I already forgot what I was writing there. ID to tile and tiles, possible edges as nums. Oh yeah, so like that's already optimized solution. So at first, what did I do? At first, I wanted to figure out the whole arrangement. I knew that it probably will be the actual task to figure the whole arrangement of tiles, so I tried to do it like constraint satisfaction problem. I decided, okay, I need to figure out an assignment where I will have a vector of rows, each row having a tile ID and transforms that we need to apply, right? And of course, we also have a little type for coordinates, which is just like row number and column number. Rows start from top, go to bottom, 0 indexed. Columns go from left to right, 0 indexed. Yeah. So I thought, okay, I will try to solve that. And I will try to solve it via mean conflicts algorithm. And I ended up with a very advanced implementation of mean conflicts. So it takes this reference to tile maps. It executes it in multiple threads. It breaks when it reaches maximal number of iterations. It increases the number of moves it allows going from low to high, multiplying by step each time. So like if you have smaller tasks, it will find the solution faster because of that. It uses taboo search to avoid stacking in local minima. And it accepts an optional hash set of corners that we know, like if we know some tile IDs that are guaranteed to be corners, we can simplify our lives with that. So the thing is, when I call this on our sample input, okay, now it doesn't really use this anymore. Let's use part 2, which still uses the algorithm. You can see that it returns very quickly. So that actually runs the mean conflicts algorithm. It runs it in multiple threads. In that find solution, it says like, yeah, in 13,634 moves, we found this solution, and that's the solution. But this is for sample input. Now, if I execute it faster, you can see that it's quite fast. Sometimes it ends up solving stuff very, very quickly. Now, I try to tune. So for example, here in 600 moves, it solved it, which is really nice. I try to tune it for the larger case. That's why it's not super fast. But if we bring down the number of iterations, actually, let me just quickly show you how it looks. So if instead of having that, I will do like, well, let's say instead of having 1000, let's do 100 as the minimum moves, breakpoint and let's multiply by 2. And let's even not put any corners. Let's pretend that we don't know the corners. Now, if we recompile it, after some second, yeah, we need part 2 sample. Oh, I actually can even also disable threading. So I will use one thread because that will be way faster for this particular thing. And I will disable taboo search. So you can imagine how much time I spent working on this thing, because I have taboo search, I have this adaptive max move strategies, I can accept corners for optimizations, I executed in multiple threads for God's sake. It's like really insanely overcomplicated solution for this task. And it doesn't work, which is funny even. Oh yeah, D20 part 2. Okay, it didn't work as well. I guess in my optimizations, it stopped being as optimal, but you can see that eventually it finds a solution. I actually really wonder why, but okay, fine. With our corners optimization, though, it's even faster. It runs like in milliseconds, hundreds of milliseconds typically, and typically finds a solution in like between several hundred to several thousand moves. Now, I will quickly walk you through what this thing does, because this is actually one of the generic constraint satisfaction solving problem algorithms, but don't do it for this task. It's not a good idea. It didn't work out well. But algorithm itself is very well known. It's known especially... It's known especially in chess for like 8-queen problems or like n-queen problems. You can see that it can typically solve it very quickly, and it's also used in scheduling problems. I actually wanted to do a video about this algorithm, but I didn't, because it's very hard to profile it and like to benchmark it, but I probably will do some simple video without like complex benchmarks about it. But yeah, so I'm using Rayon for threading this time. I decided to not do threading as I tried last time on, I think, task 16. In task 16, in the end, I fixed it. It works, the threading thing, but it required a bunch of like passing messages around, so I didn't want to spend time doing that. I also have taboo search. About taboo search, also you can check in Wikipedia. I won't go super deep into that, but essentially algorithms like min conflicts, they can get stuck in local minimums, they can get like stuck cycling the same options, moving the same things continuously. So taboo allows you to avoid that. Then corners, we will talk about them in a second, and then we have iterations, and we have max moves increase strategy. So you can see that it goes from low to high, maximum high, using step on each iteration, stuff like that. And then for each thread, we use parallel iterator to execute everything in parallel. We create random number generator, and then we call arrange. So arrange does arrangement, and then we should get like our row, we should get our corners, we should get the IDs, we can multiply them, and that will be our result. So now arrange is the core of the algorithm. It starts by generating a bunch of things that it will use. So all transformations, the size of tiles, so this is like n by n squared, so this is like n, all possible coordinates in this grid of tiles. It uses vecdeq for taboo search, because vecdeq allows you to essentially implement this like green buffer with fixed lengths very simply. It uses function random assignment to create initial random assignment, which is pretty simple, right? You create random transformation, you then create, you shuffle tile IDs, and then you just copy a bunch of things to this. You then just go essentially by row and you copy slices to the assignment vector that you will get in the end, which is a vector of rows, essentially. And here we also apply our optimization. If we know corners, we just swap them with tiles that are currently in the corners randomly as well, because we don't know which corner is which. We just know which ones are corners. So we just put them in random corners. Now, swap is important function here. It takes one assignment. Assignment is this vector of vectors of tuples of tile IDs with transformations. It takes mutable reference to assignment, and it takes coordinates, so row and column ID tuples, and then it just performs swap. So it swaps those things together. That's it. That's what we use in random assignment. We got some random assignment. We then initialize our counter of moves to 0. We then get all conflicts. So conflicts are counted. We go through all rows, we go through all columns in the current random assignment. We calculate local conflicts for each thing, for each cell, for each tile. And if they are not empty, we add them to the resulting hash map that maps each coordinate with the vector of coordinates of tiles with which it is conflicted. Now, in get conflicts, we essentially only care about left and top conflicts. We don't care about right and bottom conflicts because, well, if you don't count them, nothing changes. You just save a bunch of computation, because if you have some right conflict, it's left conflict for the next tile, you know? And if you have bottom conflicts, it's top conflict for the tile that is at the bottom. So it doesn't really matter. Here we're actually using simplicity for optimization a bit. So this is pretty straightforward. We get tiles, we get assignment, we get coordinates. We get the current tile ID, we get the current transform. We then get the tile itself. And then if we know that there is some tile on top of that, so if our row ID is larger than 0, if we are not at the top row, then we find the top tile. And then we use our top edge and bottom edge functions that use this logic from transform things that I was describing earlier to check if they're equal. If they are not, we found a conflict. We push the coordinates of the conflicted tile, so like our neighbor with whom we have conflict, to the conflicts vector. Same happens for the left tile, only we use left and right edges here. And we return the vector of conflicts we found. So we have essentially a function for finding local conflicts for some coordinates for some tile at some coordinates in our arrangement, or we can find all possible conflicts for all tiles. We have a choice essentially. Now, and we have random assignment, and we have size, and we have swap, those we talked about. And about transformation, and about tile. Okay, so we find all conflicts, and if it's empty, we solve the task. We can just immediately return the random assignment we generated. We are done. If it is not the case, and it's typically not the case, we increment our move counter. Then if we are over our max moves, we didn't find solution, we return none, and we return moves. If, however, we are not there yet, if we still can move, we select a random conflicted variable. So we get our conflicts, we choose random thing, and we got our conflicted coordinates, so all the tiles with which it is conflicted, and we get the coordinates of the tiles that is conflicted with them. We get the tile ID, we get its transformation. Then we have mutable variable improved that checks if stuff has been improved with the move. Do we actually still need it? Yeah, we need it here, I guess. But then we don't need it here because we can move it a bit closer to where it is actually used. Yeah, that's the first use of improved. So, where are we? We count the current local conflicts. So it's just the length of conflicted coordinates. And we create a local taboo list. So it's just, we take our taboo vecdeck and we just take the entries that are for the current row. And we collect them into hash set for quick comparisons. And we create a vector of possible moves. So we will generate all possible moves, and then we will evaluate and select the best one. We try first to apply all possible transformations. So we take a reference to our transform thing. We then take transform. Thankfully, it's copy type, so it will be transformed still. We then go, if the transformation is not current transformation and is not in local taboo list, since local taboo contains both style ID and transform for the current cell, we need to pass style ID here as well, but otherwise pretty straightforward. So if it's something new, then we create a new assignment where we just mutably update it, and we calculate the new count of conflicts. Then if new conflicts count is less than local conflicts count, so if we have improved something, we push this thing to possible moves. Now we don't care about resetting stuff back to the original transformation because, well, not yet, not in the cycle, because each iteration takes a new transformation anyways. Then we, after checking all of them and calculating those like possible improvements, we revert to the original transformation. And then we try to swap it with all other tiles. So for all possible coordinates, we take the another tile ID and transformation. If, by the way, that's a bit better. If another coordinate is not the current coordinates, and if it's not tabooed, we calculate conflicts for another thing, for the another tile. So we have the first tile, we take the second tile, we calculate conflicts for it as well. We then swap our tiles, and then we calculate the new conflicts count for the original tile, for the original cell, sorry. And new conflicts count for the original tile in the new position with which it was swapped. And then if we improved on both counts, we push this in as possible moves. Yeah, here I'm not sure about weighing it, but I think I won't really try to improve it further. And then after trying that, we can revert back. And then we do the same thing again. Here we need to revert because otherwise we will just start to like moving tiles around too early. We don't want to actually move stuff yet. And then we just try to find the best move. So we sort by conflicts count. Then we pop the first entry. If we got something, we and if another coordinates are not equal to current coordinates, we swap. Alternatively, we know that it was transformation change. So move only on transformation, not swapping with other tiles. Then we just assign the transformation from there. And we push it into taboo list, so to not repeat it again next turn. And we say that we have improved. If we have not improved, actually this logic then can be improved, sorry, because then we can do, can we do this? Yeah, we can. So essentially, if we have not improved, we just do a random swap to break possible ties. I think that's sufficient comment here. And then if taboo length was exceeded, then we truncate it. That's why I used vecdeck essentially because of this function. And that's why, by the way, we use push front, because truncate truncates from the back. So we push new moves in the front of vecdeck, and when we go over the size, we remove the old entries, which essentially gives us kind of like less first in, first out kind of queue. And then we update our conflicts count that we use in our while condition. So that's it. That's the algorithm relay. Now, that scene is sufficiently complex to solve our sample assignment, as I told you. So we got like really arrangement. So this is our arrangement with like all the cells. Oh, that looks like I have a bug actually. Because, no, I don't have a bug. Or do I? Because it's the same tile ID everywhere. Oopsie. I guess I broke it at some point. Well, we'll need to fix it. I want to keep it for history. Did actually? Yikes. Yeah, I guess I broke the logic. Interesting that it still allows you to solve it even with broken things. But okay, doesn't really matter. In any case, I was able to solve for sample input with that. Then I did a bunch of refactorings and probably broke something. But when I try to run it on my large input, and I will show you how it looks, but don't expect much because nothing will happen. So you see that it increases the number of iteration, it executes in multiple threads. Here, oh, I said 4. Let's do 4 threads because it's funnier. So one thing that is cool to see about that is, of course, that it will now load all my processors. So you can see that almost 400 CPU usage because of that, which is pretty cool. But sadly, apart from heating up the atmosphere, it doesn't do much yet. I ran it until it was like calculating 4 million options, and it didn't find the solution. So then, and it was calculating 4 million options on my laptop that has 8 cores. So then it was like 32 million options per iteration, and I ran several iterations. So it was like, it did a lot of calculations, believe me. Now, at some point, I was like, okay, I tried to optimize it. That's why I got taboos. That's why I got like all a bunch of things. But in the end, I figured out that I probably should have went with my original idea, which was we can encode edges as numbers to make comparing edges very, very simple. And then we have one important line in our task description. Let me find it. It's tiles at the edge of the image also have this border, but the outermost edges won't line up with any other tile. Which means if you look at data, those tiles look rather unique. And I just decided to try and convert them to numbers. And when I debug printed the numbers, I saw that they are actually unique. So like you have some matches, but they are fixed. You have fixed number of matches. And the number of matches that have less matches with other tiles, those are corners. And that's essentially what I did in the end. And that's how I found the answer for the first task, which is you just need to figure out the corners. Of course, when you know the corners, it's very easier to figure out the whole arrangement, right? Because then you can use backtracking. You can, like, if I know the corner, I can then run 4 possible, like this is arranged in 4 numbers. So it's like 4 multiplied by 3 multiplied by 2. It's factorial 4 now, which will be 20. So we need to evaluate 20 options, and we can use just backtracking. And we know that if we are going correctly, it should complete quite quickly. We can go from left to right. We can and top to bottom, and then we can use the rules that we have to figure out possible combinations. And we will have, I think, 6 options for each of those, which should work well enough for backtracking solution. But I didn't have time to write backtracking, and that's why I don't yet have the things that actually put stuff on tiles. But I got the things that figures out the corners. So in essence, what happens, I go here, I represent each tile edges as numbers. So for all edges, I just use this function edge as number that replaces dots with zeros and hashes with ones, and I interpret it as binary numbers. And I get like this tuple of two possible things, because one is just edge in the original direction, another is reversed edge, because remember, when we turn stuff around, stuff can reverse, and when we flip stuff around, it can reverse. So we got two possible numbers. But then we'll hide this for now. I actually wonder if I fix the bug, if it will work, but I'm not super hopeful at this point, to be honest. Oops. So I do this transformation, and then I have a hash map where just for each tile ID, I inserted edge numbers. And then for each entry in that hash map, so tile ID 2 edge numbers that it can possibly have, I calculate matches with other tiles. So I go through other tiles as long as they're not the same tile IDs that I have right now. And I just add to match count when I found some possible intersection. So those things are hash sets here, and hash sets have this intersection method. And that's why, by the way, in the beginning, I immediately thought about hash sets because I wrote this today. So, and edge nums are also hash sets. Actually, where do I can? This scene already returns hash set. Okay, it collects to a hash set. That's where. I intersect, and then I just do count of elements that I get remaining, and then I return it and collect it into a vector, and then I sort the vector by this count. And then I just know that I will get 4 elements with less things. So I think those on edges will have 4 matches, and those outside, not on edges, will have 6. And that's essentially the solution. I then just take this in, I take 4 first elements, I iterate, I copy them, I get tile IDs, I collect them to vector, and then I do product, and that's the solution to the task. So that's why no mean configs were needed. It solved very quickly for the first part. But second part, of course, you need to actually arrange things, and then you need to look for C-monster. And I think I will try to add backtracking there, using the corners idea to fill in the tiles. I already have the logic for moving stuff around, because monsters can be also flipped and rotated. So I also need to apply to them, but I think it will be quite easy to extend my existing logic with this dihedral group thing, and then it should be quite straightforward. But I guess I won't be doing it on the stream. Yeah, I think it's pretty obvious though how to solve it from this point on. So, second, here we go. So thank you for watching. I hope it was enjoyable. Don't forget to subscribe. Don't forget to like. Don't forget to hit the bell if you're really into Advent of Code. We will be solving more tasks. I hope to be back on Wednesday, and we will see. I will be either back on Christmas, but more likely I will be back after the Christmas on the weekend to solve the last tasks. We are very, very close to finish so far with Rust. It was quite challenging sometimes because, as you can see, you don't see stuff as easily as with Python or something like that. But it was also very fun, and my skills in Rust improved significantly. For example, this crazy code for day 20, I was writing yesterday's night and today, and I was able to pull some pretty complex stuff off very quickly. So though it didn't work, this approach, I'm quite proud of myself, and I think it was a good idea to try to do it with Rust, because now I feel almost as fluent with it as I feel with Elixir. That being said, I see you soon. Thank you for watching. See you next time.